So we were working on the Cloudy project, Cloudy workshop. So this is all modeling of interstellar gas. Our project specifically was working on PDRs and trying to model this with Cloudy. Now, I work on PDRs myself, but one of the main issues with PDR models, or not an issue, but they just make an assumption for the PDR cosmic ray background. And then this can affect the chemistry and this can affect what is viewed. So what is observed. So we want to examine this a bit with Cloudy. Cloudy is code in C++. It's maintained by Gary Furland, who's giving us this workshop. So that was wonderful to have. It solves simultaneously for ionization, radiation field, metallicity, abundances, temperatures, a whole bunch of different parameters. And it can predict what spectrum you would expect to observe from a certain region of gas. So this spectra that you see here is for M16 that we did at the beginning of the workshop. So we had to first learn how to use Cloudy and then apply this to a project in this past week. So we want to look at how PDRs are affected. One of the perks of Cloudy is that it covers the whole spectrum of light. But for PDR modelers, they just focus on the FUV, very small piece of the spectrum right here. So when we ran our models, we restricted ourselves to the FUV, and the intensity is measured in drain units, and drain unit is for the typical interstellar FUV radiation that you would expect from an interstellar cloud. We are looking at PDRs, which are on the border of OB clusters. If you don't remember, then, I mean, there was a presentation last Friday about it. So these are very, very high intensities for FUV radiation. So we fixed an FUV radiation, and then we started to examine the cosmic ray influence on the chemistry and the abundances that occurred in it. And then I think, one sec, sorry.
Yeah, I'll talk about the further results of this project on PDR. So we were interested in line emission lines or line ratios, which would be sensitive to cosmic rays. So what you see in these plots is plotted either the line intensity or the intensity ratio, as for the third plot, plotted against the cosmic ray ionization rate for different densities of your PDR cloud. And we see that HCO plus, this specific transition, and HCO plus that transition, they trace cosmic rays pretty well. And actually HCO plus is doing quite well at almost all ranges of density that we consider here. Also the line ratio H3O plus to OH plus traces cosmic rays quite well. So these are some of the lines. These are not all the lines that trace cosmic rays, but these were just some of those. And again, I repeat that for this analysis, we kept the incident or background UV field same or at a constant value, because the effect of cosmic rays could be degenerate with high UV field. So here we only look at one specific value of the UV. Then another thing we checked was to look at the traceability of dense gas tracers. So that would be the next slide. Yeah, so we knew that it has been well established that these molecules, HNC, HCN, they trace dense gas, or they trace the density of gas. And we see that for a low cosmic ray ionization rate of 10 raised minus 17, the intensity increases linearly with the density. But as we go to higher cosmic ray ionization, the trend might not be linear. So for the left two plots, it's not at all linear as you go from the blue to the green curve. But for HCO plus, it's still linear. So when one is looking for tracers of dense gas, then one should be careful with their assumptions for the cosmic rays. And that was all for the PDR project. There were two other projects, and they will talk about their results now.
Yes.